Hi, I'm Shirley Wang from Princeton Edge Lab. Today I'm going to talk about adaptive video streaming over Whitespace. Whitespace are the frequency bands that are originally assigned to be exclusively used by incumbent users, like TV broadcasting or factory use. But because those bands are not heavily loaded, as illustrated in this picture, for some frequency bands they are not used at some time or at some locations. FCC proposed that when there is no incumbent users, these channels can also be used for local wireless communications to compensate the increasing internet traffic. In our work, we consider three-tier access model for the 3.5 GHz band proposed in PCAST. The first tier are primary factory users, which are licensed and have high protection. The second tier are prioritized licensed users, like schools and hospitals. They can only use the channel when Tier 1 is absent. The third tier are unlicensed users and opportunistically access the channel. Tier 3 and Tier 2 can coexist as long as the transmitting power of Tier 3 does not interfere with Tier 2. Dynamic spectrum sharing in Whitespace was proposed to compensate the fast increasing internet traffic. From Cisco's prediction, half of the growing internet traffic is video traffic, so our work focused on video adaptation in the Whitespace model. Another reason that we study video is that video traffic is the most challenging one, because it's bandwidth consuming and also is the delay sensitive type of application. In this work, we study how video streaming can adapt to the Whitespace three-tier channel access model. Our goal is to maximize the average video quality, avoid freezing screen, and also we will try to reduce the number of video quality changes when the throughput fluctuates. Our technique is to combine two existing techniques to deal with varying channel conditions. One is a video coding technique called slew video coding. In SVC, each segment is encoded in multiple layers, as shown in Figure 1. Higher layers depend on lower layers. Consider the case that multiple clients request the same piece of video, but each client has different network conditions. For those with good network conditions, they will request all layers from the server. For those with poor network condition, they will request only the base layer. Another technique is a network adaptation protocol called Dash. Each client decides which resolution of a segment to request based on the throughput prediction. Here, for each video, the server will store multiple copies but with different resolutions, as shown in Figure 2. Currently, Dash is very popular and has been used by some video streaming agencies like YouTube and Netflix. Can we directly use Dash in Whitespace model? The answer is no, because Dash will fail when the throughput fluctuates frequently. The first two figures are the case that Dash provides good adaptation when throughput has low variation. The lower two figures show that with the same average throughput as above, but when the throughput fluctuates quite frequently, Dash can only provide low resolution most of the time and also incur frequent video quality changes. Both are bad for the quality of experience of an end user. Actually, the fast varying throughput is the case in Whitespace, and the dynamics of Tier 2 users can be predicted based on its traffic type. We combine Dash and SVC to fit the Whitespace model and design an MDP-based adaptation algorithm for scalable video coding. The current channel condition is estimated based on the measured signal strength. In the video player, we have three bins to serve as the buffer for each SVC layer. At each step, the segment selection is based on current channel condition and the segments in each bin. The goal is to maximize the MDP expected utility function. Here are some key components in our adaptation algorithm. For the adaptation part, because in Whitespace, Tier 3 throughput fluctuates frequently due to Tier 2 users' dynamic, the throughput-based adaptation in conventional Dash will not react fast enough to the throughput variation. And because the variation of 5-layer SNR of Tier 3 is the direct consequence of Tier 2 dynamic, we will use this to infer throughput. Also in conventional Dash, the video rate adaptation is reactive, meaning adaptation after throughput change. In Whitespace model, we have some information of Tier 1 and Tier 2 dynamics, either from the database or from their pre-announcement. We can use this to predict throughput in the future and do proactive adaptation. For the video part, we will use scalable video coding because we can improve the segments we have already downloaded by requesting higher layers of those segments. To avoid freezing screen, we will keep a minimum number of base layers in bins. To reduce the number of video quality change, we will always download lower layers first. And when there are enough lower layers, we will proceed to download high layers to improve the video quality. This is a toy example to compare our algorithm with Dash. In our algorithm, we have medium resolution all the time, and sometimes we have the high resolution when throughput is high. For Dash, it only provides low resolution when throughput is low, and medium and high resolution when throughput becomes better. The quality also changes more frequently in Dash, so we see that our algorithm performs better than Dash when throughput fluctuates frequently. Thanks for listening. Please refer to our paper for more details. If you have any questions, feel free to send me an email. Thank you.